Hi everyone, my name is Neha Kardam and this is the 10th lecture on electronic communications. In this lecture, we are going to learn about transmission lines. So let's get started. Transmission lines, they are used to carry electrical signals, usually at radio frequencies, a relatively short distance. They include both copper and fiber optic constructions. Fiber optics we are going to see in the next lecture. So let's see what are the different points here. So before I discuss these points, let me use another definition to explain the transmission lines. In other words, we can say that transmission line is used whenever radio frequency energy needs to be transported between two nearby points. And the purpose of transmission line is to get radio frequency energy from one point to another with minimum of signal loss. Now here it says different types of lines are used in various applications depending on frequency, power level, cost, and mechanical needs. In transmission lines, some signal is lost, and this is referred to as attenuation, and two mechanisms for loss are dielectric absorption and ohmic loss in the conductors. And then further we are going to cover the specific loss in the lecture. Specific loss of a line, it is the decibel attenuation per unit length. Specific loss depends on frequency and the type of line employed. And further we are going to cover the characteristics of all transmission lines. Is characteristic impedance, and this is very important, and we will see the usefulness of this in the coming lecture in the next coming slides. A line should normally be terminated in a resistance equal to its characteristics impedance. So when the resistance of the line of the transmission line is equal to this characteristics impedance, then we have the maximum transmission of electricity. Standing waves will result on any line driving a mismatched load. The voltage standing wave ratio is a measure of match quality. A perfect match results in a 1:1 ratio. So we're going to see this also. And then we have Smith chart. So we will learn about the Smith chart and how to calculate the transmission lines elements. For example, voltage standing wave ratio, and we can calculate the impedance, admittance, etc. Now comes types of physical constructions. So here on the screen you see four different types of the cables. First is the twisted wires. Twisted wires you see here on the top. These are inexpensive transmission line. They use both of the conductors. In here you see two conductors are used. They are of equal size and shape, and they basically make a balance with these two conductors. These twisted wires, they are closely together, which improves the shielding ability to reject any unwanted signal. This twisted wire also increases high frequency losses because the capacitance between the two wires it increases, and it above a few megahertz twisted pair of wires, they are not very useful for transmission line, and it becomes very lossy. So therefore it is not good for radio frequency transmission lines. Twisted pair of wires, they are mainly used for low frequency work, and the example for that would be the telephone lines. In telephone lines, they carry audio frequency at low frequency, and the losses in that type of line is very low. And in this type of twisted pair of wires, the characteristic impedance is between 25 and 200 ohm, and it usually depends upon the type of insulation you're using and how tightly these two wires are twisted to each other. Now next is the ladder line. So the second picture here you see of the cable is the letter line, and these are the simplest and they are lowest in the cost. The two parallel conductor you see here, they are separated by an insulating material. You must have seen the ladder lines in the TV sets. So at the back, these ladder line type of wires, they were basically used. And the characteristic impedance of the ladder line, it lies between 200 and 600 ohm. And it also depends upon how these two conductors are far apart. And both the wires you see here, they are supposed to be equal in size, means which means that the path for the current incoming and the outgoing current should be equal. So these type of letter line above 100 megahertz, you can see here their range is from 50 to 100 megahertz. So above 100 megahertz, these type of letter line, they experience loss of radiations, and they are actually poorly shielded, and any metal object nearby, it can interfere with the signal on the line. And next is the coaxial lines. Coaxial means shared access, and in this type of line, you can see at the outside we have the insulator, and then you have a copper mesh, and then you have a dielectric, and under the dielectric you have the copper. So copper right now is not very visible here, but if you open up this type of cable, then you will see a copper wire inside. So the conductor inside so the conductor here will be inside the hollow outer metal tube, and between the two conductors, so this mesh conductor and the inside conductors, you will have the dielectric is there. And this dielectric you see here, it can be made up of air, plastic, or other insulating material. So the dielectric insulate two conductors and also control electric characteristics of the line. So the two conductors you see here and the inside, they are unequal, and the paths for current going in and out are also going to be different. In coaxial cable, you see this braided outer conductor. This conductor is approximately at a ground potential. Therefore, coaxial cable they are very superior in shielding than other transmission lines. And running coaxial line next to the metal object will not cause a problem with the line. And they have a wide range of characteristic impedance also. It is in between 25 ohm to 100 ohm, and it is useful up to 1000 megahertz, which is 1 gigahertz. Now next is the hardline cables. So these hardline cables, they consist of silver coaxial cable, and this is the special type. And the metal outer jacket which you see here is of silver color, and it is very rigid and it resists any kind of bending. So these hardline, they are variation on coaxial. They are lower loss than standard coaxial cable which you saw here, but they are more expensive compared to the coaxial cable. Now next is the waveguide. So these are the examples of the waveguide you see here, and this is how they look. So these waveguides you see, they work above 1000 megahertz, and they are mainly used for microwave applications. So if you see the construction, it is a hollow metal tube that carries the ultra high frequency, or we can say super high frequency radio energy. And these waveguide wall you see here, they are made up of metal, and so that the radio frequency energy cannot escape. They are designed in such a way, and there is no center conductor or dielectric in this type of waveguide. It has coupling stub on each end for microwave radio frequency energy to travel, and waveguide can also be used to feed microwave antennas, for example horns or dishes. In that case, receiving end of the waveguide, it just opens into the dish of the antennas. These waveguides are very expensive, and the application, if we see it, it can be used in air traffic controller radar, and it's mentioned also here. Waveguide is very expensive, but it's the only solution for the certain applications such as radar. And let's read above 2 points as well. Above 1000 megahertz, waveguide becomes practical transmission line. There is no center conductor in waveguide. The radio signal travels through it by bouncing off the sides as it moves. Now next we have a transmission line. A transmission line, you see here, may look like plain wires and insulation, but it has three basic properties. First is the resistance to current flow, inductance, which is controlled by the length, and capacitance, which wires share with the ground. So this RLC, resistance, is not mentioned here, but it is present in the transmission line. So the RLC, they are ignored for DC when you're working on DC, and also for low frequency. At radio frequency, these effects no longer can be ignored. So they have to be considered. So here, let's see what it says. A transmission line can be thought of as an infinite set of infinite small inductors, capacitors, wired as shown. The inductance and capacitance are measured per unit length. Together, these distributed values determine the characteristic impedance of the line as well as the velocity of propagation. So the formula for characteristic impedance is given by this. Z naught is equals to under root L by C, and this formula is for velocity of propagation, which says Vp is equals to 1 by under root Lc. So by these two formulas you can calculate the characteristic impedance and the velocity of propagation. Now here, one small section is taken from the transmission line, and when you do the analysis, you take a small section and then you do the analysis on that particular section. And when you made a model for a transmission line, small model, then in that you have to lump all the inductance in the transmission line into one, and the capacitance of the transmission line into one. If your line is lossless, if there are no losses in the line, then in that case your resistance is ignored. So here we are assuming this transmission line is the ideal transmission line, and that's why here the resistance has been ignored. Now moving on to the next slide. Now here the definition of velocity of propagation is given, and it says when waves move more slowly down a transmission line than in free space, the speed of wave travel is also called the velocity of propagation, and it can be easily calculated by this formula, where L and C are the inductance and capacitance per unit length, and the computed velocity is in unit lengths per second. In other words, we can say that velocity of propagation is the speed at which a wave move down a transmission line. Now next here it says what is a velocity factor, and for velocity factor this formula is given. So the velocity factor is basically the ratio of the conduction speed to the ratio of speed of light in the free space. So this is the speed of light in free space, and the ratio, and let's read here. Velocity factor of a line is the ratio of propagation speed, which is Vp, in the line to the speed of it should be speed of light in free space. It is always less than 1 for real world transmission line, and most coaxial lines, they have very high frequency. They have a velocity factor between 0.6 and 0.7. Now, the example is given. What is the velocity propagation and velocity factor for a cable with inductance 255.9 nanohenry per meter and capacitance of 103.36 picofarad per meter. So we have these two values. We can easily calculate the velocity of propagation and velocity factor, just plugging the values of L and C into this equation. We'll get this, and that velocity of propagation value can be put here, and by that we can find the velocity factor. Now next is the characteristics impedance, and some examples are given here. First, let me tell you what is the characteristic impedance. It is the ratio of voltage to current at any point, and it is given by this formula: Z0 is equals to under root L by C. And it is saying what is the characteristic impedance of a line rated at 78.0 nanohenry per fit and 31.2 picofarad per fit. So the inductance and the capacitance is given. You will just put here in the values of these two and you will get the characteristic impedance. So this states that this line must be terminated in a 50 ohm load to prevent reflection of energy from the load back to the transmitter. So this reflection of energy takes place in the transmission line if the line is not terminated at a appropriate characteristics impedance load. Next is if the current at a certain point on the line is above 1 ampere, what is the voltage? So if you know the impedance, characteristic impedance, you can easily calculate the voltage. So we know the impedance is 50 ohm. We got it from here. Current is given, so we can easily calculate the voltage. Now next it says what is the input impedance of a 1 meter section of the above line if it is terminated in a 50 ohm load. So the input impedance should be equal to the Z0, which is your characteristic impedance, and when the load resistance is equals to the characteristic impedance. So in that case, your input impedance will be equal to the characteristics impedance, which is 50 ohm when the line is properly terminated. And what is the input impedance of an infinitely long section of the above line? So in that case, again, our input impedance must be equal to the characteristic impedance when the line is of infinite line. What is the input impedance of a 1 meter section of 50 ohm line if it is terminated in 75 ohm? So here, this is the value of this impedance is different than the characteristics impedance. So let's read here. Strangely enough, it isn't a 75 ohm. Depending upon the frequency of the signal and the velocity factor of the cable, the result could be anywhere between 75 ohm and 33.3 ohm. So this actually we can calculate using the Smith chart, which we are going to see further in the lecture. Now next is the specific loss. So the main source of energy losses are the ohmic loss and the dielectric loss. Let's understand what is ohmic loss. So at radio frequency, most of the current, it tends to pass through the outside surface of the conductor rather than being uniformly distributed throughout the cross-section area. And this phenomena is called your skin effect. And it becomes severe when you are working at a higher frequency. Because what happens at higher frequency, the circumference of the wire becomes much more important than the cross-sectional area, and which means that the effective resistance of the wire, it will increase as the frequency will increase. And here the dielectric loss, when this happens, the energy lost in the dielectric, it basically converts into the heat, and we know that the best dielectric is the air. And when the dielectric losses increases with frequency and are somewhat they are also dependent on the voltage being applied. and they are not they basically degrade the performance of the signal when you have the dielectric loss. Now here you see different types of cables named here, and they shows that and here these three columns basically represents the losses at different frequency levels. So at 50 megahertz you have these losses in dB, and at 100 megahertz these are the losses, and 400 megahertz you will get this much of losses for these cables. And let's read here. Manufacturer rate each type of transmission line in dB loss per unit length at specific frequencies. This loss per unit length is called specific loss. Technicians and engineers use this data when choosing transmission lines for different applications. So when you are for depending upon what you are working on, you will actually see what are the different losses corresponding to the cables, and then you will choose your you'll choose the cables for your for whatever the application you're working on. Next it says the loss in a line in dB is equal to the product of specific loss and line length. Now comes the impedance mismatch and standing waves. So our transmission line should normally be actually connected to the load, and the resistance must be equal to the characteristic impedance. If the resistance is equal, load resistance here we are talking about is equals to the characteristic impedance, it means that load is actually matched to the line, and under that condition the energy flows from generator down to the line and totally absorbed by the load. And this is the ideal case, and that is how we want it to work. And when impedance mismatch occur, then what will happen? So anytime the load resistance when it is not equal to the characteristic impedance of the transmission line, then we say that the mismatch condition has occurred. And if the mismatch is smaller, then it continue to operate normally. But if the mismatch is higher or it is bad, then transmitter final power amplifier can get damaged, and other problems can also occur. The example you see here on the screen is of a matched transmission line where load resistance is equal to the characteristic impedance, and there is no reflection into the line. So the line termination is perfectly on the line. So it says here wave energy is totally absorbed by line and no reflection. So this is the ideal case. Let's see, a matched load on a line absorbs all the traveling waves and reflect nothing back to the source. There are no standing waves in this condition. The voltage is equal at all points on the line. This situation above shown is R is equal to Z naught, means a matched load. So here this traveling wave, we need to understand what is this traveling wave. These are basically when the energy moves down in a transmission line. We can take an example. For example, if you drop a pebble in the still water of a pond, then what will happen? The waves will move uniformly, and the difference between the pond water and here in transmission line is that the movement of the wave. In transmission line, the wave is limited to move in one direction, either forward or backward, whereas in pond water it is not that case. Now the next slide. So this slide is going to explain the standing wave development and how they are basically made when the impedance mismatch occurs. So we see here on the left side the incident wave, and they are going to the load side, and here it sees a mismatch. So we can read here, wave energy reaches the load which is mismatched to the line, which causes a reflection. So you can see on the second this waveform the reflection occurs, and then the line which is made up of this green color is your reflected wave. So reflected wave moves back towards the generator. When we draw our transmission line, we basically know that on the left hand side we have a generator, and then the line transmission line basically travels, and then at the other side we have the load. So this reflected wave is traveling towards the generator side, and here the third example, it shows that how the reflected waves has further traveled, and and here the mismatch of the impedance mismatch here is of R is equals to 3Z naught, where R is the load resistance, and it is 3 times of the characteristic impedance Z naught. Now here on the right hand side you see the incident wave, and it is right now incident at a 0 degree, and there are different degrees at which it is incidented has been mentioned over here. So right now it is at 0 degree, and here it is incident at 90 degree, and here it is incident at 180 degree. So what will happen when this is incidented at a different angle? At 0 degree we observe that the reflected wave is developed like this, and the resultant voltage here, it is basically the total voltage at we can say it is a total voltage at any point on the line, which is basically the sum of the incident and the reflected voltage. And if we examine the total voltage of the line at regular time intervals, then we see an interference pattern which is forms between the two waves, which is shown over here. So we'll get here. Let's first see. This is the resultant voltage, and for this wave, this will look like this, and let's see here when the incident traveling wave is incident at 90 degree, and then we find that the resultant voltage is higher, and we know that this is the sum of the reflected and incident wave, and in this case it is higher. And the third case, when it is at incident wave is at 180 degree, then this is red one. The red line you see here is the resultant, and this green one is your reflected wave. So finally we get this pattern like this of the waves for different angles. And here this is the 15-volt peak voltage value is given, and here at the negative side the peak is 5 volts. And these standing waves you see, they are basically the outgoing and incoming waves which are meeting each other and causing their voltage to add at some point and subtract also at each other, and the resulting is our standing wave, which is normally not what actually we want in our transmission line. Let's read here. Energy flow in two direction as on a mismatched line. The interaction between the two traveling waves forward and reverse produces the standing wave pattern, which we have seen here. The voltage standing wave ratio is the ratio of maximum to minimum voltage along the line, and it should be 1:1. The higher the voltage standing wave ratio, the worse the mismatch, and most applications should have a voltage standing wave ratio less than 1.5:1. So this is the way to check how your transmission line is. If it will be perfect if you have this 1:1 ratio, and it should be less than this value. Now next is measuring the voltage standing wave ratio. And voltage standing wave ratio we can basically measure using the wattmeter, And here we use special type of wattmeter. We will be using directional wattmeters, and directional wattmeters, they are an instrument designed to measure standing waves on a transmission line. And these directional wattmeter is connected between a transmitter and a transmission line, or between the transmission line and a load. So it measures the radio frequency power flow between its input and output connectors. And case A, which we see here, it yields to most accurate reading because the reflected wave does not have to undergo the transmission line loss to be measured. But whereas in the second case, which is the measuring standing wave ratio at the antenna, so in this case the standing wave ratio shows a lower value, measured load at the transmitter. If losses in the transmission lines are high, then the standing wave ratio is going to be much lower. So these are the two cases: when it is close to the transmitter and when it is away from the transmitter and you have a transmission line in between. And these are the real directional wattmeters which you can use. And if you want to work, you will basically there is an option called a sensor select here, and this is the power range which you can select. So first, if you want to use this directional wattmeter, you will click on the sensor select button corresponding to the system under test is selected, and there are 3 independent directional RF sensors, each covering a different frequency range. So you will select on that, and then you will further when you select the power range here, after that first sensor select and then the power range, and then you will basically move the knob of this function to the calibration position, and then you will use this calibration knob. It is adjusted to full scale reading. The instrument is reading the incident voltage, and this is being calibrated as 100% scale. And with the transmitter still keyed, the function knob you see here, you can, after that you can move this function knob to the SWR, which you see here, standing wave ratio position, and the meter, now it will read the standing wave ratio on the bottom meter scale, you can see here. So this one with the red line will indicate your standing wave ratio value. Now to measure the voltage standing wave ratio, we use a directional wattmeter. It is inserted at either end of the line. Insertion at the load yields to the most accurate result. Since transmission line losses attenuates the reverse wave as it moves back towards the signal source. Now next is how to calculate the standing wave ratio. So standing wave ratio can be calculated using this formula. So we need to know this formula. This is the reflection coefficient given by this, and it is equals to ZR minus Z naught divided by ZR plus Z naught, where ZR is basically your load impedance and Z naught is your characteristic impedance. And further it says the magnitude of the strength of the reflected voltage is simply the product of incident voltage and the reflection coefficient. So the reflected voltage is given by this equation, and then you can further calculate the maximum voltage, which is the sum of incident voltage and the reflected voltage. And in place of reflected voltage, you can put this value. When you put this value, this is the absolute sign, and when you put this value, then you can get this result. Same way you will do it for minimum voltage, and it can be calculated like this, and you will get this result. And then standing wave ratio can be calculated. We know that it is the ratio of maximum voltage upon minimum voltage, and if you put both the values, then you will get this result, which is in terms of reflection coefficient. Now here, important point to remember, like how we can basically remove the impedance mismatch, or we can say that what are the solution to impedance mismatch. So there are a couple of solutions. First could be radio frequency transformer you can use, which will step up or step down an impedance, or you can use a capacitor. Capacitor can be added to cancel an unwanted inductive reactance. You can also use the inductor. An inductor can be added to cancel an unwanted capacitor reactance. So all these solution you can use to avoid the impedance mismatch. Now next is the Smith chart. A Smith chart, it is used by the manufacturers to characterize the impedance of a radio frequency system on data sheet, and this Smith chart helps us in determining the multiple parameters, for example impedances, admittance, reflection coefficient, noise figure, gain contour, mechanical vibrations, etc. So on the screen here you see this origin. This origin represents an impedance which is equal to the characteristic impedance of the system, and here this line you see here, it is the real axis of the chart, and it is where all the pure resistance will be plotted. So all the pure resistance you will plot on this line. And the center of the axis you see is this is the origin, which again represents a pure resistance of Z0. And next is this distance scale. Distance scale is in wavelength fractions, and one complete circle, if you do on a Smith chart, it is the same as moving a half wavelength, which is 180 degree on the transmission line. So I'll say it again. So this distance you see, it is, if you do a complete one cycle on the chart, it is same as moving a half wavelength 180 degree on the transmission lines. Now next here you see these circles, they represent the constant resistance circles, and they are shown like this. And if you want to plot the inductive reactances, for that, this upper part of the graph, this represents the positive inductance reactance, and the graph here below is for the constant capacitive reactance, and it is shown by this blue color, and the constant inductive reactance is shown by this red color. So this inductive reactance is going to be above the real axis, and this capacitive reactance is going to be below the reactance curve. Now plotting points on the chart. To plot the points on the chart, the first thing you need to do is to normalize the impedance, and to normalize the impedance you will be using this formula which says Z dash, where this Z dash is the normalized impedance, and this is equals to Z by Z0, where Z is your actual impedance value and Z0 is the characteristic impedance of the system. Now note here, we reverse the process when we interpret points on the chart. The point values are multiplied by Z0 to get back into the actual ohm values. So we will see that in the example problem. And then next step is to find the real portion on the real axis and follow the intersection reactance circle up for XL and down for XC, and plot the points. So this is an example. Plot the following pure resistances on the Smith chart for a 50 ohm system. So here 50 ohm is our characteristic impedance, and we are going to plot for these three values. First is the 50 ohm. So we are going to find out the normalized impedance for this 50 ohm. So for 50 ohm it is going to be 1, because it is going to be divided by the characteristics impedance, and it will come out to be 1. And for 25 ohm it is going to be 0.5, and for 75 ohm it is going to be 1.5. So we know that pure impedances, they are going to be plotted on the real axis, and we know this is the real axis. And on this real axis, 25, if you see the normalized impedance 0.5, let's first see this first case 1, when this is 1, and in that case your impedance will be shown over here at this point, and this shows 1 normalized impedance. And for the second case is 0.5, and it will be over here. And for 75 ohm it is 1.5, and it will come somewhere around here. So you will mark all these pure resistances on the real axis. Now let's further see the example. Now plot the following points assuming Z0 is equals to 50 ohm. Again here this is our characteristic impedance, and we have to plot for 50 ohm, J50 ohm, negative 50 ohm, and 25 plus J25 ohm. So we are going to normalize it. When you normalize, you will basically divide by the characteristic impedance, and here you will get 1. For this case you will get J1. For this case you will get negative J1, and for this case you will get 0.5 plus J 0.5. So we are going to plot all these into the Smith chart. So let's first see the characteristic impedance. So this is here 50 ohm, and normalized impedance is 1, so that's why we have put it here. For J50 ohm, we know that this is inductive reactance, so it should be above the real axis. So it is going to be over here. If you look into the Smith chart, then you will find this J 50 ohm over here, and you will basically use this point based on this J1 ohm. So here you will have, if you see closely, this is 0.9, so after this comes the 1, so that's why we have pointed over here. And similarly, if it is the case for the capacitive reactance, then we know that it is going to be below the pure below the real axis, so that's why it is here. And you can see there after 0.9 the 1 will come, so this point represents the negative J1 reactance. And then we have 25 plus J25 ohm, and its normalized value is 0.5 plus J 0.5. 0.5, we know that this is a pure resistance, so it should be on the real axis. So we will find out that where it is going to be. So somewhere here, here you see this is the 0.5. And then to find out the complex, this whole value, what we are going to do is we are going to look in this direction for J 0.5. So first we basically select the point here 0.5, which is the pure resistance, and then you will move here and you will look here for the inductance, inductive reactance. So inductive reactance here I see is 0.5, and it lies in the same circle. So after that you can see this point, and where this represents 0.5 plus J 0.5 ohm reactance. Now next is finding the voltage standing wave ratio on a line, and these are the three steps to find the voltage standing wave ratio. First, you will plot the load impedance on the chart. Second, using the origin as the center, draw a circle on the chart that passes through the point, and here the point is our real axis. So finally read the standing wave ratio where the circle crosses the real axis. So we're going to see voltage standing wave ratio with this example, and here the characteristic impedance is given 50 ohm, and for each three cases we are going to see. So for 50 ohm, we know that this is the pure resistance. It is going to lie here at the origin, and here we don't have to actually draw the circle because the voltage standing wave ratio is going to be 1:1. For the second case, we have 75 ohm, and in this case the pure resistance is going to be 1.5. So if we plot here, and with respect to this origin, if we draw the circle, then again it will basically comes at this point, and which is 1.5. So you will have 1.5:1 ratio. Now next is 475 minus J50. First you will divide it by 50 ohm characteristic impedance, and if you divide, then you will get 1.5 minus J1 ohm impedance. So to plot that 1.5, you will find over here somewhere here in here you will get 1.5, and then negative J1, you will basically look for that negative J1. So you will search here, and somewhere here, if you see here, this is 1.0, so negative 1.0 will come in this at this point. So you will mark that point, and then from the center you will start drawing the circle. So when you draw the circle, then at whichever point it will pass here on the real axis, that will be called your voltage standing wave ratio. And in this case, you will, if you read, then it will come around 2.4. So the voltage standing wave ratio for this case is 2.4:1. Now next is the finding input impedance, and these are the three steps to find the input impedance. First is plot the load impedance on the chart and draw the standing wave ratio circle. Second, find the electrical length of the line. And third, move clockwise on the standing wave ratio circle and read the resulting impedance. So for that, I have taken an example using the Smith chart to calculate the input impedance of the circuit, which consists of 112.5 ohm load and a 1/4 of wave section of a 75 ohm transmission line. So first we are going to normalize the impedance, and here it is given 1/4 of the wave section of the 75 ohm. So we are going, this is going to be our characteristic impedance, so we are going to divide it by this load, which is the actual load impedance, and after dividing you will get 1.5 plus 0j. So you will plot that over here. It is going to come here 1.5, and that will be your point A. Now so we plot the impedance on the chart. Next we then draw the standing wave circle and move the clockwise 1/4. So if you divide this will come out to be 0.25. So so you will, when you move clockwise from this point, then here you will get 0.25 of the wavelength, and this 1/4, you can also say that this is basically the 180 degree, and so you basically if you move 180 degree, then you will get here, and then after that read out the normalized impedance at the end of the 1/4 wavelength arc, and denormalize the reading. So when you come here, then you mark this point as B, where point B is the input impedance of the line. So you will write that write the value of the input impedance. So in this case, at B, our input impedance will come out to be 0.7 plus 0j. 0j because it is on the real axis, so that's why we have pure resistance, and it will be represented by this. Now we want to denormalize this value, and we want to read it, so we can do by multiplying this value by characteristic impedance. So when you multiply by characteristic impedance, you will get 52.5 ohm. So this is how you calculate the input impedance on a Smith chart. And you can also calculate the admittance using the Smith chart, and that will be as a research topic for you. Now the summary of the lecture. I'll just quickly read all these points. First, it says transmission lines come in many shapes and sizes. Factors that governs the choice of line include frequency range, cost, and mechanical characteristics. Important electrical characteristics of transmission lines include characteristic impedance, velocity of propagation, and specific loss. Voltage standing wave ratio is good indication of the quality of impedance match between a line and a load, and ideally it should be 1:1 ratio it should have, and values above 1.5:1 may need to be troubleshoot. The Smith chart is a graphical tool for doing calculation with transmission lines. It allows a relatively easy visualization of the effect on load, line length, and other variables. So this is the end of the lecture. Thank you so much for watching.